Hello friends, welcome you all to the fourth lecture of function analysis and its applications. In this lecture, we will discuss the vector spaces and subspaces with examples. These are the contents of today's lecture: vector space and its examples, subspace and its example. Vector space. This is also known as linear space. An algebraic structure V F plus dot consisting a non-empty set V, a field F, a binary operation plus on V, that is plus such that V cross V to V, defined by if U and V are the elements of V, then U plus V belonging to V, and external mapping multiplication dot such that F cross V to V defined by A into V belonging to V for all A scalar and V belonging to V, that is vector, is said to be vector space or linear space over the field F if the following axioms are satisfied. First, V plus is an abelian group and external compositions satisfied as follows: A into U plus V equal to AU plus AV. Second, A plus B U is equal to AU plus BU. Third, multiplication of two scalar A, B, multiplication with vector, that is A into B, U, and multiplication identity 1 U is equal to U. Okay, where A, B belonging to F and U, V belonging to V, that is AB scalar and UV as vector. The vector space over the field F generally denoted by VF. The elements of V are called vectors and the elements of F are called scalars. If F is equal to R means set of real number. In the above definition, then the space is known as real vector space. If F is equal to C, that is field of complex number. In the above definition, then space is known as complex vector space. For example, R over the field R is vector space. R over the field Q is also vector space. C over C, C over R, C over Q are also vector spaces. Noting point: every field is vector space over its any subfield. Example: Q over R is not vector space. Why? If we take two elements of Q, then after addition, the result also belonging to Q. But if any element of R multiplied with the element of Q does not gives the element of Q. For example, we can see, suppose 1 is the element of Q multiplied by root 2 belonging to R. Then root 2 into 1, that is root 2, not belonging to Q. Hence, external composition not satisfied here, violating the scalar mapping. So, QR is not a vector space. The vector space of all ordered n tuples over a field F. This is the important example of vector space. Explanation. Let F be a field. A vector alpha is equal to n tuples of scalar a1, a2, a3 and so on an is called the n tuples over F. Let V be the totality of all ordered n tuples over F. Now we shall give vector space structure to V over the field F. That is, we have to check the all conditions of vector space. For this, we define the equality of n tuples, addition of two n tuples and multiplication of n tuples by scalar as follows. Equality of two n tuples, two elements alpha, a1, a2 and so on an and beta equal to b1, b2 and so on bn of V are said to be equal if ai is equal to bi for all I is equal to 1, 2, 3 and so on n. Means a1 is equal to b1, a2 is equal to b2, a3 is equal to b3 and so on an is equal to bn. Then we say that the vector alpha equal to the vector beta, addition of vectors alpha plus beta is equal to n tuples of alpha plus n tuples of beta, then alpha plus beta equal to a1 plus b1, a2 plus b2 and so on an plus bn, where a1 plus b1, a2 plus b2 and so on an plus bn are all elements of F. Therefore, alpha plus beta belonging to V. Scalar multiplication composition in V over F. We define A alpha, A belonging to field F and alpha as vector n tuples of a1, a2 and so on an. Then A alpha defined as a1, a2 and so on an. These elements are elements of F. Therefore, A alpha belonging to V. Now, we shall prove V is vector space. Means we have to check all the conditions of vector space. Associativity of addition in V. Let alpha is equal to a1, a2 and so on an, beta is equal to b1, b2 and so on bn, and gamma is equal to c1, c2 and so on cn in tuple. Then alpha plus beta plus gamma equal to n tuples of alpha a1, a2 and so on an plus n tuples of beta b1, b2 and so on bn plus n tuples of gamma c1, c2 and so on cn. Okay. So, as per addition of two vectors, that is a1 plus b1, a2 plus b2 and so on an plus bn. Again, we can add third vector c1, c2 and so on cn. So, we can write a1 plus b1 plus c1 as this, a2 plus b2 plus c2 and so on an plus bn plus cn. That is, these are in n tuples also. So these n tuples can be written as a1 plus b1 plus c1 together, a2 plus b2 plus c2 together, and so on, an plus bn plus cn together. Therefore, a1, a2 and so on, an in tuple plus another tuple b1 plus c1, b2 plus c2 and so on, bn plus cn. So b1 plus c1, b2 plus c2 and so on, bn plus cn can be written as beta plus gamma, and a1, a2 and so on, an as vector alpha. So alpha plus beta plus gamma equal to alpha plus beta plus gamma. That is, associativity of addition of vectors is satisfied. Commutative law. Under addition, we have alpha is equal to n tuples of a1, a2 and so on, an. Beta is equal to b1, b2 and so on, bn. Then alpha plus beta, that is a1 plus b1, a2 plus b2 and so on, an plus bn. All members of this n tuple as scalar, so we can write a1 plus b1 as b1 plus a1. a2 plus b2 can be written as b2 plus a2 and so on, bn plus an. So as per definition of n tuple, we can write beta plus alpha. This is as vector of beta plus alpha. Therefore, alpha plus beta is equal to beta plus alpha. So commutative law holds. Existence of additive identity. We have I is equal to n tuples of 0, 0, 0 n times belonging to V. This is the additive identity of addition. If alpha is equal to a1, a2 and so on, an, then alpha plus I, that is n tuples of a1, a2 and so on, an plus 0, 0 n times as n tuple. So a1 plus 0, a2 plus 0 and so on, an plus 0 in tuples. So a1 plus 0, that is a1, a2 plus 0, that is a2 and so on, an plus 0, that is an. That is alpha. So alpha plus I is equal to alpha. Thus I is equal to 0, 0, 0 n times is the additive identity in V. Existence of the additive inverse. If alpha is equal to n tuples of a1, a2 and so on, an belonging to V, then beta is equal to minus a1, minus a2 and so on, minus an belonging to V, such that alpha plus beta equal to a1, a2 and so on, an plus minus a1, minus a2 and so on, minus an equal to a1 minus a1, second member a2 minus a2 and so on, nth member an minus an, that is n tuples are 0, 0, 0, that is identity. So we can say that the tuples minus a1, minus a2 and so on, minus an is the additive inverse of vector n tuples a1, a2 and so on, an. Hence, ordered pair V plus is an abelian group. Further, we observe that A belonging to F, alpha is equal to A1, A2 and so on An, beta is equal to B1, B2 and so on Bn belonging to V. Then A alpha plus beta, where alpha plus beta as vector and A is scalar. So we have to check the properties of scalar multiplication with vector. That is, first property of external composition of vector space, A into alpha plus beta is equal to A value of alpha plus beta, that is A1 plus B1, A2 plus B2 and so on An plus Bn. That is A1 plus AB1, because here we have the property A alpha equal to AA1, AA2 and so on AAN. So we can multiply this scalar A with n tuples of A1 plus B1, A2 plus B2 and so on An plus Bn as A into A1 plus B1, A into A2 plus B2, A into An plus Bn, that is A1 plus A B1, A2 plus AB2, AAN plus ABN. That is, this is addition of two vectors AA1, AA2 and so on An as n tuples, and another vector in n tuples AB1, AB2 and so on ABN. That is the addition of these two vectors. This can be written as A1, A2 and so on An plus A into B1, B2 and so on Bn. That is, we can write this A alpha plus A beta. That is the property of vector space, this satisfied. Now we have to check another these three properties. Next property of external composition, if AB belonging to F and alpha belonging to V, then we have to check A plus B alpha equal to A alpha plus B alpha. Let us check it. A plus B into alpha, A plus B into n tuples of A1, A2 and so on An equal to A plus B. A plus B as scalar, so we can multiply with all members of n tuples. That is A plus B A1, A plus B into A2 and so on A plus B into An. That is AA1 plus BA1, another AA2 plus BA2 and so on AAN plus BAN. That is, we can write these n tuples as addition of two vectors, that is AA1, AA2 and so on AAN plus another n tuples BA1, BA2 and so on BAN, as like this. And this n tuples can be written as A into n tuples of A1, A2 and so on An plus B into B1, B2 and so on Bn. That is, this expression can be written as A into alpha plus B into alpha. That is, the property A plus B into alpha is equal to A alpha plus B alpha whole. Third property, if AB belonging to F and alpha equal to A1, A2 and so on AN belonging to B, then AB alpha equal to AB into tuples A1, A2 and so on AN. So AB A1, AB A2 and so on AB AN can be written. So scalar A can be written as outside the tuple. So A we have in tuples BA1, BA2 and so on BAN. So this can be written as A into B alpha. That is third property of external composition hold. Next, one is the unit element of F. If alpha equal to A1, A2 and so on AN, then 1 into alpha equal to 1 into n tuples of A1, A2 and so on AN, that is 1 A1, 1 A2 and so on 1 AN in tuples. That is, this can be written as in tuples A1, A2 and so on AN, that is alpha. Hence, 1 is the multiplicative identity. Hence, all conditions of vector space over the field F are satisfied. Hence, we can say that the given examples vector space of all ordered n tuples over the field F as vector space. Noting point, the vector space of all n tuples F will be denoted by V and F also. Sometimes we also denote it by Fn F. Here the 0 vector is the n tuples 0, 0 and so on. Next example, the vector space of all polynomials over a field F. Explanation, let Fx denote the set of all polynomials in one variable x with scalar coefficient. Then Fx is vector space over the field F with respect to the addition of two polynomials and the product of polynomial by a constant polynomial as scalar multiplication. Let Fx is equal to summation I ai xi equal to a0 a1x plus a2 x square plus and so on. If we take the polynomial of order n, so we can write I is equal to 1 to n. Fx is equal to summation I ai xi, gx is equal to summation I b into xi, hx is equal to summation I ci xi, be an arbitrary member of Fx, then the equality of two polynomials Fx is equal to gx if and only if ai is equal to bi. Suppose Fx is equal to gx, it means summation ai xi equal to summation I bi xi, that is a0 plus a1x plus a2 x square plus and so on is equal to b0 plus b1x plus b2x square and so on. So we can compare the like coefficient of the power of x, that is a0 is the coefficient of x to the power 0, this is the b0 is the coefficient of x power 0 of gx, that is a0 is equal to b0. Similarly, coefficient of x is a1 in fx and coefficient of x is b1 in gx, then a1 is equal to b1 and so on. So we can write if fx is equal to gx if and only if ai is equal to bi for all I is equal to 0, 1, 2 and so on. Addition composition. fx plus gx equal to summation ai xi plus summation bi xi. So this can be written as summation ai xi plus bi xi. That is summation ai plus bi into xi. Since ai plus bi for all I are the elements of f, therefore fx plus gx is the element of fx, and thus fx is closed with respect to the addition of polynomial. Okay, scalar multiplication in fx over f. Suppose k be any scalar, that is k belonging to f, we have k fx, that is k into summation from I is equal to 1 to up to order of polynomial ai xi. So this is a scalar, so we can write summation k ai xi. Since k ai are the elements of f, that is scalar, therefore kfx belonging to fx, and thus fx is closed with respect to the scalar multiplication. Means scalar multiplication with the element of vector, that is vector. Here kfx is the element of fx. Now we shall show that fx is vector space for these two compositions. Commutative law. Commutative law, we have to check fx plus gx is equal to gx plus fx. So proof is very simple. Fx summation I ai xi plus summation I bi xi. This can be written as summation I ai plus bi xi. This can be written as also interchange the position of ai and bi because scalar. So summation I bi plus ai xi. Again we can write summation I bi xi plus summation I ai xi, that is gx plus fx. Hence fx plus gx is equal to gx plus fx. That is commutative law hold. Associativity of addition in fx. Fx plus gx plus hx can be written as summation ai plus bi plus ci xi. Okay, and this bi plus ci can be written together. Therefore summation I ai plus bi plus ci into xi we can write. Hence this expression can be written as summation ai into xi plus summation I bi plus ci into xi. This expression and this expression can be written as fx plus gx plus hx respectively. Hence fx plus gx plus hx equal to fx plus gx plus hx. That is associativity of addition in fx hold. Existence of additive identity in fx. Let 0 denote the 0 polynomial over the field f. That is 0 equal to 0 plus 0 into x plus 0 into x square plus and so on. Hence we can say that 0 is the element of fx, that is 0 as a vector. Therefore 0 polynomial is the additive identity. existence of additive inverse of each member of fx. Let minus fx be the polynomial over the field f. Minus fx equal to minus and summation I ai xi. Summation I ai xi is the value of fx. So this is minus 1 ai also a scalar. So this can be written as summation I minus ai into xi. Minus ai also as a scalar. So minus fx can be defined in polynomial. Then minus fx belonging to fx, and we have fx plus minus fx, that is 0. 0 means 0 polynomial. Hence we can say that minus fx is the additive inverse of fx. Thus fx is an abelian group with respect to the addition of polynomial. Now for the operation of scalar multiplication, we make the following observations. If k belonging to f, then k into addition of two vectors, that is k into fx plus gx. So we can write k summation I aixi plus summation I bxi equal to k summation I ai plus bi xi. K is scalar, so we can write summation I ki plus k bi xi. Hence we can write this as summation I kai into xi plus summation k bi into xi. So k is scalar, so we can write k outside from both summation. So we can write k summation I ai into xi plus k summation I into bxi. Hence this can be written as k fx plus this as kgx. That is k into fx plus gx is equal to kfx plus kgx. And second property of external composition, k1 plus k2, that is addition of two scalar multiplication with vector. So k1 plus k2, here summation I ai xi, that is value of fx, equal to summation I k1 plus k2 ai xi. This can be written as k1 ai xi plus summation I k2 ai xi. Therefore k1 independent from I, k2 also independent from I, so we can write outside the summation. That is k1 summation I ai xi plus k2 summation I ai xi. That is k1 fx plus k2 fx. That is the second property of external composition, k1 plus k2 into fx equal to k1 fx plus k2 fx. Third property, k1 k2 belonging to f, then k1 k2 fx equal to k1 k2 summation I ai xi. This is the value of fx, equal to summation I k1 k2 ai xi. Again we can write k1 k2 ai xi, that is k1 summation k2 ai xi. that is K1 into K2 fx. K2 ai as scalar. So K1 K2 fx is equal to K1 K2 fx. Fourth property of external composition. If 1 is a unity element of the field f, then 1 into fx equal to 1 into summation aixi, that is summation 1 into ai into xi, that is summation ai xi can be written as fx. So 1 into fx is equal to fx, that is 1 as a multiplicative identity of the vector space. Hence fx is vector space over the field. We can prove so many examples of vector spaces. Some examples we have as follows. This set V of all m cross n matrices with their elements as real numbers is a vector space over the field F of real numbers with respect to the matrices as addition of vectors and multiplication of matrix by scalar as scalar multiplication, also satisfied. But if the set of all m cross n matrices with their elements as rational number and F is the set of real numbers, then V will not be closed with respect to scalar multiplication. Suppose we have m cross n matrix. Okay, their elements as rational numbers, but field here R. If any elements of real numbers multiplied with rational number, that is real number. So elements of m cross n matrix does not satisfy the condition of vector. For example, root 2 belonging to R and alpha belonging to V, then root 2 alpha not belonging to Q. Therefore, VF will not be a vector space because the multiplication of scalar with vector is vector fail. Next example, let X be a non-empty set and F be any field. Let AXF denote the set of all functions from X to F. The two functions F, G belonging to AXF are called equal if Fx is equal to Gx for X belonging to X. Then AXF is vector space with the operation of addition and scalar multiplication defined as follows. F plus G X is equal to Fx plus Gx and Cfx is equal to C into Fx for X belonging to X, where C is the element of F. All conditions of vector space are satisfied. Next example, let F be any field and a sequence in F is a function sigma from positive integer to field F. The sequence sigma such that sigma n is equal to an. For n is equal to 1, 2 and so on denoted by an. Let V consist of all sequences an in F that have only a finite number of non-zero terms an. If an and bn are in V and t belonging to F defined as follows: an plus bn equal to an plus bn and external composition with vector t into an equal to tan also belonging to V. With these operations, V is vector space. So it can be proved as above. Next example, let V equal to R square over R. The component wise addition A xy defined as 3axy for all xy belonging to R square and A as scalar belonging to R. Then V is not a vector space over R, because here the property of external composition A, B, U not equal to A into PU. All conditions are satisfied, but this condition is not satisfied. Why? Taking left hand side, A, B, U as order pair XY. So AB into U, that is AB XY. As per this definition, we can write 3AB XY. Right hand side, this ABU. So ABU can be written as 3BXY and again multiply with scalar. So 3A into 3BXY, that is 9AB XY. Hence, left hand side not equal to right hand side. So, this vector defined as V is equal to R square with this definition, it is not a vector space. Next example. Let V is a set of all real polynomials of degree n is not a vector space over R with usual addition and scalar multiplication of polynomial. Explanation. Let fx is equal to x to the power n and gx is equal to minus x to the power n belonging to V. Both are the polynomial of degree n. Then fx plus gx is equal to 0. The polynomial 0 has no terms at all and is called the zero polynomial, because the zero polynomial has no non-zero term. The polynomial has no degree, that is 0 not belonging to V. Thus, V is not closed with respect to the usual addition of polynomial. Hence, V is not a vector space over. Next, subspace. A non-empty subset W of vector space V over a field F is called a subspace of V if W is a vector space over F with the operation of addition and scalar multiplication defined on V. That is, if V is a vector space and W is subset of V and satisfies the all condition of vector space, then we can say that the W as a subspace of vector space V. In any vector space V, 0 and V are always subspace of V. These are known as the trivial subspaces of vector space. Theorem. Let V be a vector space over a field F and W be a subset of V, then W is subspace of V if and only if the following three conditions hold for the operation defined in V. That is, non-empty set belonging to W, and if X belonging to W and Y belonging to W, then X plus Y also belonging to W, and C belonging to F and X belonging to W, then Cx belonging to W. These two conditions can be written in combined way. So we can write for any xy belonging to W and the scalar A and B belonging to F, the linear combination Ax plus By belonging to W. For example, if a vector space V is a set of all real valued continuous function over the field F of real number R, then so that the set W of solution of the differential equation is a subspace of V. Solution. We have W, y satisfies this equation. 2 d2y by dx2 minus dy by dx plus 2y is equal to 0. Obviously, if y is equal to 0, okay, satisfies the given differential equation and such belonging to W and W not equal to 5. Here y 0, that is we have y is equal to 0 as a solution. So W non-empty. Now let y1, y2 belonging to W and AB belonging to R as a scalar. Then by above theorem, we should show that ay1 plus by2 also belonging to W. That is the solution of the given differential equation. Okay, y as here ay1 plus by2 as solution of this differential equation, that is we can put at the place of y. So 2 d2y by dx2 ay1 plus by2 minus ddx of ay1 plus by2 plus 2 ay1 plus by2. So 2 d2 dx2 of y1 plus 2b d2 dx2 of y2 minus 9a d dx of y1 minus 9b d dx of y2 plus 2a y1 plus 2b y2. So grouping the terms gives a 2 d2 y1 dx2 minus 9 d dx of y1 plus 2y1 plus b 2 d2 d2y2 dx2 minus 9 d dx of y2 plus 2y2. That is a into 0 plus b into 0 equal to 0. Thus, a1 plus by2 is solution of the given differential equation and so it belongs to W. Hence, W is subspace of V. Next example. Let CR denote the set of all continuous real valued functions defined on R. Clearly, CR is a subset of the vector space ARR, which is defined in above example 8 for x is equal to R, f is equal to R here. We claim that CR is a subspace of ARR. Explanation. First note that the 0 of ARR is the constant function defined ft is equal to 0 for all t belonging to R, because constant functions are continuous. We have f belonging to CR. Moreover, the sum of two continuous functions is continuous and the product of the real number and continuous function is continuous. So CR is closed under addition and scalar multiplication. Hence, CR is subspace of ARR by the above theorem. Next, this subset S equal to order pair A square, where A belonging to R is not a subspace of R square because it is neither closed with respect to the scalar multiplication nor with respect to addition. So we can write here as example 2 as scalar and 1 as order pair. Okay. So 2 1 1, that is 2 2. Here order pair defined A square. Here this one 1 into 1 square 1. But if you write 2 2, this is not 2 2 square. Okay, that is 2 into 1 1, not an element of. So the scalar multiplication with vector is not a vector. Similarly, if S equal to order pair AB, A and B are the elements of R, that is order pair AB belonging to R square, B greater or equal to 0, then S is not a subspace of R square because it is not closed with respect to the scalar multiplication, because minus 1 into 0 1, we have 0 minus 1. Okay, this is not belonging to S because here B greater or equal to 0, but here this is negative. So this subset is not as a subspace of vector space. So in this lecture we have discussed vector spaces, subspaces and their examples. These are the references which have been used in this lecture. Function analysis, Dover publication by George Beckman and Lawrence Naressi. Introductory functional analysis with applications, John Valley, written by Erwin Krejcik. Next, function analysis, third edition, New Age International Publisher by B.V. Lemieux, and function analysis by Waterwood. Thank you.